In this video, let us discuss about linear programming problem. We all come across many target-based situations in day-to-day life. Say, for example, a student has to complete a project within 15 days. Say, person has to achieve a sales target within a month. Another person wants to buy a gadget within rupees 25,000. In all these cases, what is the objectives? In the first case, student want to achieve a maximum score within 15 days. Objective of a person who wants to buy a gadget is minimize the cost. She wants to buy a gadget within her budget of rupees 25,000. And the salesperson wants to achieve a maximum target sales within a month. So here the objective is, in the first case, student want to achieve a maximum score. In the second case, salesperson want to achieve a maximum target. In the third case, they want to buy a gadget within a minimum cost of rupees 25,000. So these are the objective here. So either here in these three cases, we come across a situation like maximizing the cost or minimizing the cost. In the second situation, we come across is the constraint. In this case, student wants to complete a project within 15 days. In the second case, salesperson wants to achieve a target within a month. In the third case, they want to buy a gadget within rupees 25,000. So these are called as the constraint. So we see in these three situations, there is an objective as well as there is a constraint. So this type of problem can be solved with the help of linear programming technique. Linear programming technique helps us to find an optimum solution for a given problem. Let us begin our discussion with a problem. Here is a problem. A furniture dealer deals only with two items, table and chairs. He has rupees 50,000 to invest and has storage space of at most 60 pieces. A table costs rupees 2,500 and a chair costs rupees 500. He estimates that from the sale of one table, he can make a profit of rupees 250 and that from the sale of one chair, a profit of rupees 75. He wants to know on how many tables and chairs he should buy from the available money so as to maximize his total profit, assuming that he can sell all the items which he buys. So this kind of problems can be mathematically modeled. So before modeling a problem, we need to first analyze the problem. We need to first understand the problem. So then we can formulate this problem. So after formulating the problem, we can find the optimum solution to this problem. So here, let us denote the table by the variable x and let us denote a chair by the variable y. Since here we want to maximize the profit, when we were reading through this line, we understood that he wants to maximize the profit. So our objective here is to maximize the total profit. So we come across this problem, we saw that a table would cost rupees 2,500. So X number of table would cost rupees 2,500 into X. Similarly, a table cost rupees 500 for the furniture dealer. So Y number of table would cost 500 into Y. And we saw here that he has only rupees 50,000 to invest. So that is the first constraint. He has only 50,000 to invest. So that can be considered as a constraint regarding to the investment. So which can be represented mathematically as 2,500 into X plus 500 into Y lesser than or equal to 50,000. And next we come across here that he can store at most 60 pieces. So this is regarding to the storage constraint. So whether it is a chair or table, he can store only 60 pieces. So hence the the second constraint is with respect to the storage. So X is the number of table and Y is the chair. So we can represent this as X plus Y lesser than or equal to 60. This is less, we are putting here lesser than or equal to because he can store only at most 60 pieces. So hence it becomes X plus Y lesser than or equal to 60. So coming to the objective function. What is the objective here? Here, the furniture dealer objective is to maximize the total profit. So that can be represented as maximize Z is equal to, so as a table cost rupees 250 and a chair cost rupees 500, and then here we notice that by selling one table he makes a profit of rupees 250. So by selling X number of table he makes a profit of 250 into X. Similarly, by selling one chair, he makes a profit of rupees 75. So the total profit by selling the table can be written as 75 into Y. So this is the objective function. And then here X represents the table and Y represents the chair. So that can be represented as X greater than or equal to 0 and Y greater than or equal to 0. So now we have formed this way of representing the given situation is or given problem is nothing but modeling of a problem or formulating the problem. So now we have formulated mathematically the given problem in this way. So it comes first is the objective function, and then this objective can be achieved subject to the constraints. So here the constraints are the investment constraint and the storage constraint. So now suppose, let us think that a furniture dealer wishes to invest only on table. Let us think that before solving it mathematically, let us think that a furniture dealer wants to invest only on table. Then he has 50,000 to invest. So 50,000, and then for him a chair would cost rupees 500. So therefore divided by 500. So because a chair would cost him 500, so hence we have divided the total amount by the cost of a chair. So then we get by cost of the chair. So therefore we get here 50,000 divided by 500. So it becomes here 100. So now within the money whatever he has, he can invest on 100 chairs. Even though he can invest on 100 chairs, because of the storage constraint, he cannot invest on 100 chairs. He has to forcibly invest only on the 60 chairs, even though he can buy 100 chairs, but because of the constraint of the storage space, he can only invest his money on 60 chairs or 60 pieces. With this, he would get a profit of 60 into 75 because a chair would give him a profit of rupees 75. Therefore, the total profit he get is 60 into 75, so which would be equal to rupees 4,500. So again, let us think that instead of chairs, let us think that since he can invest on let us since he can invest on table as well as chairs, and he can store at most 60 pieces. So let us think that he would invest on let us think that he would invest on 10 tables, and then he would invest on 50 chairs. Let us think that he would invest on 10 tables and 50 chairs. So then what is the profit he will get? 10 into 250, because this satisfies the storage constraint, because he can invest on 60 pieces. So therefore 10 tables and 50 chairs is nothing but 60 totally. So therefore this whatever we have thought, this would satisfy the storage constraint. But what would be the profit? So let us calculate that. So it becomes 10 into 250 and 50 into 75. 50 into 75. So totally we get, when we add this, multiply and then add, so we will be getting rupees 6,250. Okay. So suppose he is not interested only on chairs. He is not interested on 10 tables and 50 chairs, but he is interested to invest on only tables. So in that case, how let us see what would be the profit. So he has got rupees 50,000, and then a table would cost rupees 2,500. So totally we get this as equal to 20. So then the profit, let us see what is the profit he would get. So table would give him a profit of rupees 250. By selling a one table, he get a profit of 250. So by selling a 20 tables, he would get a profit of rupees 5,000. But we cannot go ahead in doing this way by trial and error process. So we can solve this by applying the linear programming technique. So this problem, I will let us see how we can solve this problem by applying the graphical method. There are various techniques. So for today's class, let us see how we can solve this problem by applying graphical method of solving the linear programming problem. So there are certain procedures. Okay, so those procedures are listed in this way. In the step 1, it says represents the given problem in mathematical form. That is what we have done here. We have represented the given problem in the mathematical form. That is nothing but we can say this as formulate the linear programming model. Represent the given constraints as equalities on x and y coordinate plane, and identify the feasible region by drawing the graph of all constraints. The feasible region is the intersection of all the regions represented by the constraint of the problem. The step 3 says the feasible region obtained in step 2 may be bounded or unbounded. Compute the coordinates of all the corner points of the feasible region. So step 4 says select the corner point obtained in step 3 that optimizes the objective function. And then at last, the step 5 says we can go ahead for interpreting the results. So according to the given algorithms or the steps listed in the previous slide, let us discuss how we can obtain this solution. So as we have looked into earlier, so this problem can be formulated mathematically in this manner. So maximize z is equal to 250x plus 75y. This is the objective function, and the constraints are so 5x plus y. So we have simplified here. So this was 2500 into x plus 500 into y lesser than or equal to 50,000. So this can be simplified as 5x plus y lesser than or equal to 100. So that it is easier for us to solve a problem. So constraint is the first constraint is regarding to the investment constraint, that is 5x plus y lesser than or equal to 100. The second constraint is the storage capacity. So x plus y lesser than or equal to 60. And here since x is the table and y is the chair, so x can be written as greater than or equal to 0, y can be written greater than or equal to 0. So as the step 2 says, so step 2 says represent the given constraint as equalities on x and y coordinate plane. So hence, so let us, this is the inequality whenever it is a lesser than or equal to or greater than or equal to, all that type of equations represents the inequality. In order to solve the problem, so let us represent this in terms of equality condition. So 5x plus y is equal to 100. So we want to know only the xy coordinate. So hence let us take x as equal to 0. So when you take x as equal to 0, we get y as equal to 100. Similarly, let us put in the second case, let us take y as equal to 0, so that x will be equal to 20. So we got here when x is that can be represented in the xy coordinate system. So when x is 0, y is equal to 100. Similarly, when y is equal to 0, x is equal to 20. So let us join that point. So we get a line. So that is represented here in blue color. So this is with respect to the equation 5x plus y is equal to 100. Let us consider the second equation. The second equation is x plus y is equal to 60. So again, we want only the coordinates which intersects the x and y axis. So hence, let us take x as equal to 0, so that y will be equal to 60. Similarly, when y is equal to 0, x is equal to 60. So let us join those points with a straight line. So here the green color line represents the constraint x plus y is equal to 60. So here this line represents the constraint x plus y is equal to 60. And the blue color line, whatever I have marked here, so this represents the constraint, investment constraint, that is 5x plus y is lesser than or is equal to this. The constraint is lesser than or equal to, but we have converted in terms of equal to and taken the coordinate points. So that is equal to 100. So according to the step 3, then let us see the feasible region. Okay. So feasible region is, as we stated here in the procedure. So feasible region is the intersection, or you can also call it as a common portion of all regions represented by the constraints of the problem. This is nothing but the feasible region. So once again, let me say, the feasible region is the intersection, or you can call it as a common portion of all regions represented by all constraints of the problem. So if you see, there are here two constraints. So if you see, the common portion is the intersection of all the points is this point, this portion. So here, so I can say O, A, and then B, and then C as the feasible region. So this is what we have studied in the step 3. So then let us come back to step 4. What's the step 4 says? The feasible region obtained in step 2 may be bounded or unbounded. So in this case, the feasible region obtained is bounded. So we can see it is bounded. So then what is it says? It says The step 3 says compute the coordinates of all the corner points of the feasible region. So we want to find the coordinates of all the corner points of the feasible region. So this is 0, 0. This corner O represents the position 0, 0, and A represents the position 0, 60, and C represents the position 20 and then 0. But what about B? So if you're drawing in a graph sheet, you can find the coordinates of B directly. So, but if you're not drawing in a graph sheet, you need to solve this two equations. What are the two equations? So B lies at the intersection of 5x plus y is equal to 100, and then x plus y is equal to 60. So B lies at the intersection of these two lines. So there are so many methods to solve this type of simultaneous equations. So, but we can easily solve it by elimination method. So subtracting the first equation by the second equation, we get 5x minus x is equal to 4x. And 100 minus 60, which would be equal to 40. So hence, on solving, we get x as equal to 10. So once you know x, substitute in any one of the equations so that you can find y. So it is easy to substitute in the second equation. So if I substitute, x plus y should be equal to 60. Since we know x as equal to 10, y must be equal to 50. So the B lies at the coordinates 10 and 50. So now we know all the corner points. So there is a theorem. What the theorem says, I'm not going to discuss the proof of this theorem. This theorem already you might have studied in your 12th standard. So this theorem says that if R is the feasible region, that can also be called as convex polygon for a linear programming problem, let z is equal to ax plus by be the objective function when z has an optimum value. So optimum value means it can be either maximum or it can be a minimum value, where the variables x and y are subject to the constraints described by linear inequalities. This optimum value must occur at a corner point of the feasible region. This theorem says optimum value must occur at a corner point of the feasible region. So making use of this theorem, so there are n number of points in this feasible region which are the solution for the given functions, for the given objective function. So but based on the theorem, we can consider only the corner points of this feasible region, as this corner point would give us the optimum solution. So I have made a table here. The corner points are 0, 0, 0, 60, 10, 50 and 20, 0. So corresponding to this, let us find the z value. What is z? Z is the objective function, so which is defined as 250x plus 75y. So let us put here in the place of x 0 and in the place of y 0. So the value of z would be 0. So in the next case, let us take x as equal to 0 and y as equal to 60. So 75 into 60, we would get rupees 4,500. Similarly, with respect to the third corner point, let us take x as equal to 10 and y as equal to 50 in this objective function. We would get the objective value that as 6,250. So similarly, let us substitute the last corner point, whatever we have considered, that's the point C. So C lies at x is equal to 20 and y is equal to 0. So when we substitute that x as equal to 20 and y as equal to 0, we get rupees 5,000. So for all these corresponding values, we notice that rupees 6,250 is the maximum value. So hence we can say that the maximum profit a furniture dealer would get is rupees 6,250 by investing on 10 tables and 50 chairs. So this is how we can solve the linear programming problem graphically.